Okay, we'll get started. أول كل سنة وأنتم طيبين برعاية الخير. I mean, عيد مبارك سعيد. I was actually on the air, I was flying from Orlando to here during the Eid, so it was a long trip. But anyway, it's not a way to end your day with biochemistry, especially with a heavy lecture. Good news, bad news. Good news, some of these slides you've seen before in mold. Okay, the bad news, we're going to get into more details, and there's going to be more requirements in terms of what to know, what not to know, because you are now at a higher level. So we get to torture you high at the higher level as well. For the objectives, the listed in the slide, we do expect you to know basically the role of cholesterol as a substrate for the steroid synthesis. And we do expect you to know the steroid synthesis pathway, including the pregnenolone and progesterone. Then we will talk about the natural synthetic steroids, especially glucocorticoids and mineralocorticoids, and why we use certain ones rather than the others. Clinical features of congenital adrenal hyperplasia, which we studied in year one, but we'll just go in more detail, especially the 21 alpha hydroxylase deficiency and the 11 beta hydroxylase deficiency. And of course, the principles of therapy for congenital adrenal hyperplasia. So what are hormones? Chemical messengers, as simple as this. That's the definition of hormones. They're a way for cell-to-cell communication. That's why we have the hormones. 4 major hormones, classes of hormones. Steroid hormones, estrogen, progesterone, peptide hormones, insulin as an example, amino acid derivatives, epinephrine as an example, prostaglandins and related compounds, PGE2 as an example. We're going to discuss today steroid hormones in particular. And of course, no one likes to discuss steroid hormones because there's so much details about the steroid hormones. So we do have hormones. They're classified basically into different groups, steroid hormones, but they do play key roles in carbohydrate regulation, such as glucocorticoids, mineralocorticoids, and gonadotropins. That we already know. They do play a role not only in the carbohydrate mineral balance or productive functions, but in inflammatory responses, stress responses, bone, metabolism, cardiovascular fitness, behavior, cognition, and bone. They usually get transported because of the fact that they're hydrophobic in nature. They get transported bound to certain globulins, such as the corticosteroid binding globulin, which binds cortisol, substeroid binding globulin, which also in this case binds testosterone, estradiol, allows basically transport through the circulation. These are the slides I'm going through right now. These are all review slides. I mean, you should by now you know the information. The glucocorticoids, mineralocorticoids, androgens, estrogen, progestogens. These are all types of steroid hormones. Cortisol versus cortisone. You know the difference, right? Cortisol is what? Active. What about cortisone? Is the active actually? Cortisone is an active metabolite of cortisol. What do we use for treatment? Cortisone. So cortisol is what is being synthesized in our body, gets converted to cortisone, and we do give cortisone as for the treatment. How do we synthesize it? Which organs are involved in steroid biosynthesis? Well, we have the adrenal cortex. Do you know which hormones or steroid hormones are synthesized by the adrenal cortex? Aldosterone, androgens as well, right? So we have also the testes, ovaries, and some peripheral tissues, adipose tissue, the brain. Adipose, estrogen or estrone. The estrone, right? And the estrone gets converted to estrogen. So we do, these organs are responsible for the synthesis of steroid hormones. And one thing about the steroid, they're not stored or packaged. Once they're synthesized, they get released right away. And are there genes coding for steroids? What do you think? Steroid. Do we have genes like insulin? Yes, with enthusiasm. No. We don't have genes for steroids, but we have genes for the enzymes that synthesize steroids and can make the steroids. That's how you look at it. Okay? So steroid hormones, they're non-polar, we said that, and could easily diffuse through the lipid membranes, and they do have typical or share typical ring structure because of the fact that it's from cholesterol, right? So peptide hormones, such as insulin, there are specific genes, whereas steroid, no, we don't have genes for it. They're synthesized from enzymatic modifications of cholesterol. So you have cholesterol, enzymes that will modify the cholesterol and make the different steroid hormones. Thus, we have limited number of steroids. Okay, whereas for the other hormones, we have plenty because of the fact that each of the peptide hormones is coded by one of the genes. How do we transport and the steroid hormones, and how do they exert their effect at the molecular level? As we indicated, they get transported in circulation bound to certain carrier proteins. But these steroid hormones need to be unbound first, where they would penetrate the plasma membrane because of the fact that they're hydrophobic in nature. So they would penetrate. There are two mechanisms of signaling. We have the NES and the MES. NES is the nuclear initiated steroid signaling, going this way, or the MES, membrane initiated steroid signaling, this way. Here we can have either cytoplasmic receptor or nuclear receptor. Both belong to the NES, nuclear initiated signaling, steroid signaling. The MES, on the other hand, is membrane mediated, and this is a quick response where we talk about seconds to minutes. Here we're talking about hours to days in terms of response by the steroid hormones. They will get inside the cell, bind the DNA, initiate transcription and translation of proteins, and this is how steroid hormones exert their effects. Now, as we indicated, all are derived from cholesterol. They're not packaged, synthesized, released immediately. They're basically converted or produced in the mitochondria and the smooth endoplasmic reticulum. Now, where do we get the cholesterol to synthesize the steroid hormones? We have three pools. The first one, de novo synthesis. The cells could synthesize the cholesterol. 1, 2. LDL. The LDL could deliver cholesterol. That's why we call it bad cholesterol. Does the LDL have cholesterol? Yes. Again, I keep telling you, when you take the reading of LDL, HDL, what are you measuring there? It is the cholesterol in the LDL, cholesterol in the HDL. We want the cholesterol to be in the HDL. Why? Because then the HDL will take it back to the liver from the peripheral tissue to the liver. We get rid of it. Whereas LDL would deliver it to the tissue. And what's your third pool of cholesterol by which the cells could synthesize the steroid hormones?
The gonads?
The stored esters, cholesterol esters. So we have three that the cells could utilize it. And we'll see that there are some cells would rely on the LDL cholesterol. Others would rely on the deep biosynthesis as well. Right? So the rate limiting step for steroid synthesis is a protein called steroidogenic acute regulatory protein STAR. And we'll come back to this in the next, not the next slide, the slide after. So the organs responsible for the steroid hormone synthesis would include adrenal cortex, as we indicated, and we do have three regions. And I'm telling you right now, I don't know why every time we have endo, they would ask these questions. Which zone? There's synthesis of cortisol is by which zone? Synthesis of androgens, aldosterone, whether in anatomy, physiology, they will put these questions. So we do have three zones: the glomerulosa, fasciculata, and reticularis, and we do have basically a function in terms of the steroid hormone being synthesized by each zone in the adrenal cortex. Aldosterone is basically in the glomerulosa, cortisol, fasciculata, and androgen is by reticularis. Corpus luteum and ovaries, of course, progesterone and estradiol. Testes, testosterone and dihydroxytestosterone. What's the difference between testosterone and dihydroxytestosterone? Which one is more important? Dihydroxy, right? But why do we always talk about testosterone?
Higher concentration?
What do you think? Usually, actually, the dihydroxytestosterone is in conditions for itself, rather than physiological conditions. Well, it's more important actually, the dihydroxytestosterone. But what's the difference? I'll show you how it's synthesized, so at least you would understand what's going on. Let's start with the biosynthetic pathway. Let's take it stepwise, trying to get you to the more complicated one. So we have cholesterol, precursor. We have the progestins. Let's try to memorize this slide because we're going to get into the next level, then the next level. Progestins. From progestins, we can synthesize glucocorticoids, mineralocorticoids, and androgens. Then we have the estrogens. So are we saying that the female produce androgens, the male sex hormones? Yes. Yeah. They get converted to estrogens. Getting into a complicated pathway. So we said the foods. This is basically, let's say this is the testes or ovary. We have extracellular lipoprotein, and then we have de novo synthesis, by which we have acetate to synthesize cholesterol. How do we synthesize cholesterol? Condensation of acetyl-CoA, right? So we utilize acetate. In addition, we have cholesterol ester pool by which we get cholesterol from as well. Now, we have the luteinizing hormone, which would activate, would convert or produce cyclic AMP. Cyclic AMP acts as messenger, right? The messenger would activate protein kinase A. That will affect the star protein. And what's the star protein? Did you remember it? It's the rate limiting step, basically. So what does it do? It allows the control to get into the mitochondria. This is where steroid synthesis would occur. So now the star is would regulate the rate limiting step, which is the uptake of cholesterol into the mitochondria. Then the cholesterol is being converted to pregnenolone, progesterone, androstenedione, testosterone. The cholesterol being utilized basically or synthesized to pregnenolone utilize an enzyme called cytochrome P450 side chain SCC cleavage. So cytochrome P450 side chain cleavage SCC. Another name is dismutase or CYP11A1. Why do I need to put three names for you? Because it depends on the textbook. And I've seen some of the exam review questions, USMLE, some use dismutase, some use CYP11A1 or SCC. And I actually, last year, I used also one of these things. I'm just telling you that. Of course, you cannot repeat them, so that's all. What I'm saying is that these names, this is a critical step, basically, and somehow I always see they're asking about the SCC, the side chain cleavage protein or enzyme that will convert, what's the function? Converts cholesterol to pregnenolone, progesterone, and then we have androstenedione, and then testosterone. There are key enzymes, pregnenolone to progesterone, 3-beta, hydroxy steroid dehydrogenase, androstenedione to testosterone, 17-beta hydroxy steroid dehydrogenase. To make it simpler for you, forget about this, I would study this slide. I will not ask you about structures. Okay? But why do we need to know this slide? Because I'm going to show you how, when there's a deficiency of an enzyme, why would we see that there are two, for instance, when we have deficiency of 21 alpha hydroxylase, CYP21A2, for congenital adrenal hyperplasia. So when we see a deficiency here, for instance, what happens? Well, this goes here, but we have the same enzyme here and here. So you would get deficiency in aldosterone, you would get deficiency in cortisol. But this would push this pathway to basically more estrogen, more androgens. Right? The same here, if we get deficiency here, why do we get hyper versus hyper tension? So this is key so that you would understand the concept of steroid hormones, how it's complex it is. So what do we need to know? Basically, as I said, the previous slides is just to drag you to this slide. If I were you, I would skip the previous slides, just focus on this slide. No structures, nothing. Let's try to review it, try to see what is important. Okay? We have cholesterol. What's the first intermediate metabolites going to be synthesized from cholesterol? We said SCC, pregnenolone. Pregnenolone would go for progesterone. Then let's follow the aldosterone, mineralocorticoids. Progesterone, deoxycorticosterone. Corticosterone, aldosterone. Why do I need to know this? Because when you ask for analysis for certain metabolites to diagnose the congenital adrenal hyperplasia, some of these will be your diagnostic metabolites that you can say that this patient has whether 21 alpha hydroxylase deficiency or 11 hydroxylase deficiency. So let's go again. Cholesterol, pregnenolone, progesterone, deoxycorticosterone, corticosterone, aldosterone. We know what's the function of aldosterone? Is what? Retention of salts, chloride in particular. So if you see that there is high aldosterone, what happens? Hyper. So if you have low aldosterone, No sodium. So what happens? So hypo, right? What happens to the potassium? Hyper. Why? Because it will try to compensate. Okay? Now, if you look into the other pathway, we said progesterone, 17-hydroxyprogesterone. Deoxycortisol, cortisol. So you can see here there's basically an enzyme responsible to take the progesterone to deoxycorticosterone, 11-deoxycorticosterone. And the same enzyme, the CYP21A2 or 21-alpha hydroxylase, will convert either the progesterone to deoxycorticosterone or the 17-hydroxyprogesterone to 11-deoxycortisol. Right? So if you have a deficiency, because we're going to talk, I highlighted for you in actually red here, the two enzymes that are responsible for congenital adrenal hyperplasia. 21-alpha hydroxylase and the 11-beta hydroxylase, right? So if we have inhibition of the pathways for 21A2, CYP21A2 or 21-alpha hydroxylase, what happens? Which one is expected to increase? To increase in terms of diagnostic value. 17-hydroxyprogesterone. This will increase because it's not going that way. But what happens to it? It goes this way as well. So what do you expect is going to happen in this pathway? So we have three arms: aldosterone, cortisol, estrogen, and androgens. Right? So you have here, both are blocked. Aldosterone synthesis, cortisol synthesis. So what do you think the androgens and estrogens going to happen? Going to go a high increase. How do we diagnose 1-alpha hydroxylase deficiency? Measuring 17-hydroxyprogesterone. I've seen these questions several times in USMLE review exam books. What is the diagnostic test for the 17-beta? I'm sorry, for the 21-alpha hydroxylase deficiency? What's the percentage of deficiencies of 21-alpha hydroxylase deficiency versus 11-beta hydroxylase deficiency? 95%. So 95% of the congenital adrenal hyperplasia comes from deficiency of 21-alpha hydroxylase. Okay? Now, question, why do we have hyperplasia in the first place? Congenital adrenal hyperplasia. So, we said this pathway is stimulated by ACTH, right? Now, do we have a negative feedback mechanism? This is deficiency here. So, but in particular, the cortisol, the one that would inhibit the ACTH. So, cortisol is inhibited. As a result, we have hyperplasia, adrenal hyperplasia. Let's review it again. As I said, I want to show you how complex it is. It's not that simple. We have three arms, and the three arms, you can see here, it's pushing for two arms, either up or down, and the other arm is different, is separate. So we have, again, cholesterol, pregnenolone, progesterone, deoxycorticosterone, corticosterone, aldosterone. The key one that we have adrenal hyperplasia, where we have 21-alpha hydroxylase deficiency. The same time, the same enzyme is responsible to convert the 17-hydroxyprogesterone to deoxycorticosterone, cortisol. This is diagnostic, high level, basically, for congenital adrenal hyperplasia, right? Now, you block here, what happens? We're going to go this way. Androstenedione, testosterone, or estrone in the adipose tissue. testosterone by aromatase. Also need you to know the aromatase or the CYP from P450-19. CYP19 is the aromatase. Aromatase is responsible for conversion of testosterone to estrogen. Estrone, adipose tissue. So adipose tissue, so that when we gain weight, whether male or female, we have enlargement, breast enlargement. So estrone is produced by adipose tissue, and then it gets converted to estradiol. Okay? What about no, that's different pathway. Okay. What if we have deficiency of 11 beta hydroxylase, CYP11B1? So we have 21A2, we have 11B1. The oxycorticosterone is going to increase, right? And we're blocking here. We have deficiency in aldosterone. What about here? We have deficiency in cortisol. So now, if we block here, what happens to the aldosterone? Goes down. Hypo or hypertension? Hypo, right? What if we block here? Hyper. We said, if we block here, we're blocking aldosterone synthesis, cortisol synthesis. So we end up with hypo, right? And diagnostic is 17-hydroxyprogesterone. What if we do block or inhibit if there is inhibition at the 11 beta hydroxylase? So we have 11 oxycorticosterone. Aldosterone has weak effect of aldosterone. As a result, we have salt retention, we have hypertension. Does it make sense? Okay. So we have deficiencies in both the cortisol, corticosterone, and then we have also increase in gonads and estrogen. Gonads steroid hormones. So which enzymes I need to know? Right? Everything I want you to know, I already talked to you about. The side chain cleavage enzyme, displase. What's its function? Cholesterol to pregnenolone. The 3-beta hydroxysteroid dehydrogenase, 17-alpha hydroxylase lyase. No, you know what? You can skip these two. We'll just focus on one. 21 hydroxylase, 11 beta hydroxylase, right? Aromatase. I'm happy with that. I'll give you a discount this time. So these I've seen many questions related to them. That's why I'm asking you to know them, right? This is just the same pathway. Just focus on the enzyme that I told you about, and here, which one what is indicated in the circle here? The 17-deoxyprogesterone is for diagnosis of 21 alpha hydroxylase deficiency. What about the deoxycorticosterone? Diagnostic of 11 beta hydroxylase deficiency. That's what you would order for diagnosis. Okay, I will study this one because the rest is just elaboration of the same pathway. What I care about here, in the adrenal cortex, what are the steroid hormones being synthesized by the adrenal cortex? Aldosterone, cortisol, testosterone, estrogen, estradiol as well, to some extent. But so we have sex hormones, aldosterone, cortisol, and this is the dihydroxytestosterone coming from the testosterone. So all what I mean, this is the same slide as previous. Just want to show you that in the adrenal cortex, the 3 hormones are synthesized. Aldosterone, sex hormones, cortisol. That's what you need to know from this slide. What about here? Okay, you're talking about synthesis of testosterone, estrogen, ovaries, testes, and estrone, adipose tissue. It's the same slide. Just want to show you what each organ or which one is responsible for the synthesis of these steroid hormones. So we have testes, ovaries, and adipose cells. Cholesterol all the way. We have testosterone. This ends up in the testes right here. Then the testosterone gets synthesized or converted into estradiol, and this is basically in ovaries. Androstenedione can be also converted to estrone, and this is basically in both male and female adipose cells. In obese men, overproduction of estrogen in fat cells could cause gynecomastia, where there's excessive male breast development. Okay, so we know that what steroid hormones are synthesized by the testes and the ovaries. Let's look into which specific cells are synthesizing it. You can really summarize each slide in one sentence or two sentences. If you know that pathway, that's all what you need to know. In the testes, what did we say we synthesize? Which hormones in particular? Testosterone. And we know that two main parts that the testes is organized into two main parts: seminiferous tubules, interstitial tissue, and the interstitial tissue basically is responsible for steroid synthesis, and that is in particular the Leydig cell. So which cell is responsible for steroid synthesis? And the testes, this is the Leydig cell. I would put just one sentence. Okay? What about, it's the same here. The ovaries. We do produce estrogen, we already know that. Mainly which is estradiol. Progesterone and androgens. Largely relies on LDL as a source of cholesterol for steroid synthesis, and it's usually secreted primarily from the ovarian follicles and corpora lutea. This is just the follicle, just to show you which cells basically in the ovaries would produce the steroids. We know that it is composed of, this is the follicle, composed of oocytes, granulosa cells, and theca cells. So which cell would produce it, the granulosa cells or the theca cells? Or both? Or they help each other? This is the model that tells you basically because of the fact that the theca cells, the granulosa cells do not basically lack what? The androgens needed are not made by the granulasa cells. What happens? The theca cells would synthesize it, and then the androgens would be converted to estradiol, and this is by the granulosa cells. But after all, this is just a hypothesis. So you do realize here the take-home message. Two cells are needed for the synthesis of estradiols. Theca cells and the granulosa cells. Would synthesize the androgens, and then the granules will synthesize the estradiol. That's the summary of these two slides. Okay. Cortisol. We know that they have multiple effects. Well, we're done with the steroid synthesis and so on. So this is basically a repetition of what we just studied, but we're going to try to re-emphasize key points or repeat some of the points we just mentioned. We know that the cortisol has different effects in terms of glycogenolysis, memory, gluconeogenesis, skeletal muscle breakdown, lipolysis, immune depression, circadian rhythms. If you were to order cortisol, what's the time you would request the sample to be taken? 7 o'clock in the morning, right? 6 to 7, usually 7 o'clock. Why? Because it has, is it the highest or the lowest? The peak, 7 to 8. And then what happens? It goes down, lowest secretion around 2 to 4 a.m. basically. So we have diurnal effect on cortisol. So when you order cortisol levels, sample collection is around 7 to 8 a.m. to capture the peak. Okay? Now, look into this slide. What do you see? Corticosteroids, right? Some are synthetic. Are these synthetic?
I think it's low.
Fludrocortisone,
Oh, they're all.
hydrocortisone, dexamethasone, come on. They're all synthetic glucocorticoids, right? And you have prednisolone. Actually, I published a paper about dexamethasone, prednisolone, hydrocortisone. Yeah, that was 3 of them. We have paper in terms of their effects as anti-inflammatory glucocorticoids. The hydrocortisone, dexamethasone, prednisone, cortisone. Then you have the fludrocortisone. What's the difference? Look at the structure. Have you ever wondered which one I would use, which one I would not use?
This one.
Steroid 2 affects anti-inflammatory effect and salt retention effect for each one. Usually, they utilize the hydrocortisone as one in terms of its effect. So, the hydrocortisone, anti-inflammatory effect, sodium retention effect, 1-1. Then, what about the prednisolone? Well, it has mild of anti-inflammatory effect. Look into dexamethasone. 30 times compared to the hydrocortisone in terms of anti-inflammatory effect. Does it have an effect in terms of sodium retention? No effect. What about the aldosterone? No anti-inflammatory effect, but it has sodium retention effect. What about fludrocortisone? Has good anti-inflammatory effect, around 15 times compared to the hydrocortisone. But what else it has? Salt. So, but we have aldosterone. Why don't we use aldosterone for treatment when we have deficiencies of aldosterone? Half-life is basically very low, 20 minutes. So we cannot use it for treatment for the deficiency of aldosterone. As a result, we use what? Fludrocortisone because it has higher half-life. Right? So now you know what's the difference. When do you use one rather than the other? Dexamethasone versus hydrocortisone, and so on. And prednisolone, you can see that prednisolone is also 4 times similar to the other ones. The one with the higher anti-inflammatory effect is the dexamethasone that's usually used when you have severe cases of inflammation. You would use the dexamethasone. We talked about congenital adrenal hyperplasia. We talked about why do we have the hyperplasia in the first place. Cannot secrete aldosterone electrolyte disturbances. We have hyponatremia, hyperkalemia, and depending on where the effect is. One thing we did not mention in terms of the 21 alpha hydroxylase deficiency, what happens? We're putting progesterone to 17 alpha hydroxyprogesterone, right? We said this is the diagnostic metabolites for 21 alpha hydroxylase deficiency. Androstenedione, and then in the peripheral tissues gets converted to testosterone. So we have virilization for females and precocious sexual development for male. This is the same slide, no difference. We talked about, this is blocking, the 21 alpha hydroxylase deficiency. Everything I said, we have hypovolemia and shock in severe cases because of the fact there's salt and water loss. And then we have hypovolemia and shock, neonatal adrenal crisis in the case of 21 alpha hydroxylase deficiency. Now, the diagnosis, we said 17 hydroxyprogesterone as early as 4 days after birth. This is the diagnostic metabolite. And basically, increased stimulation of androgens production will lead to virilization in the baby girls and precocious puberty in boys. When there's partial enzyme defect, late onset form, menstrual irregularities, and hirsutism in young females. Diagnosis, basically, at least 2 days after birth, you would see increased 17 hydroxyprogesterone. And if it's late onset of 21 alpha hydroxylase deficiency, this could require corticotropin stimulation test. Why? Why would you go for corticotropin stimulation test if it's late onset? Usually, in endocrinology, how do we diagnose diseases? By using stimulation tests. So if you stimulate, if you give a corticotropin into the patient, what happens? This would increase the 17 hydroxyprogesterone. Right? If you see there's no increase, that tells you that it's not 21 alpha hydroxylase deficiency. 11 beta hydroxylase deficiency, we talked about it, and we talked about in terms of the salt retention, hypertension, and we said this is because of what? The 11 deoxycorticosterone increase, which has similar effect to mineralocorticoids, aldosterone. We said for the treatment of deficiency of aldosterone, what do we give? We give fludrocortisone. Why? Because of the fact that aldosterone half-life is 20 minutes. So you cannot use it for treatment. As a result, we give fludrocortisone, which has similar in terms of effect, sodium retaining effect, relation to its anti-inflammatory action as well. And this basically we could use it for the treatment of Addison's disease. Okay. God, I feel like I lost you guys. I have 3 people sleeping in the front, but I like this. She was like sleeping, and then wake up and ask, like, was she sleeping or she was awake? I have no idea. Anyway, you have any question? Thank you.